Okay, today we'll be discussing ANOVA, which is analysis of variance. But what we are looking in this video is just only one single factor, that is analysis of variance with one single factor. Okay, assuming we have this table. We have this table. Okay, we have analysis of variance with one factor, with two factor, with replication, without replication, and we also have a missing value. But in this case, there is nothing like missing value. We are looking at one single factor experiment. Okay, assuming we have a A here, we have B here, we have C here, then like this. Okay, so let's do it this way. Okay, this is a one factor experiment we are considering, one factor. So we have A, B, C. You can see this is the, according to the row we have the treatment. Now the column we don't have anything, and that is why we call it one factor experiment. Okay, in this box now, say we have A11, A12, dot dot dot, A1n. Then here we have let me use small b, B11, B12, dot dot dot, B1n. Then here we have C11, C12, dot dot dot, C1n. So now this is the factor. We have one factor, and that is why we call it one single factor. So the factor here is A, B, C. So in this regard now, for us to get what's it called, the variation between treatments, so we are going to need variation between treatments. Variation between treatments. Variation between treatments is given as we have a B summation J dot into bracket X bar J dot minus X bar all square. So this is the formula to get the variation between treatments. And what do you mean by this Xj dot? Xj dot means the mean of each treatment, the mean of A, the mean of B, the mean of C. That is what we mean by Xj dot. All right, we also need variation within treatment. Variation within treatment is given as summation J dot K into bracket Xj dot K minus X bar J dot all square. So what do we mean here? We have Xj dot K, and what we mean by Xj dot K is each value in this box, each value in this box represents Xj dot K, then minus X bar J dot. Now it means each value here minus the mean of the first treatment plus each value here minus the mean of the second treatment, and so that's how we have this. Alternatively, we can say variation within treatment to be equals to let me put it this way, total variation minus variation between treatment. Yeah, we can say total variation minus variation between treatment. All right, then the total variation is given as we have summation J dot K into bracket Xj dot K minus X bar all square. X bar all square is the total mean, the mean of all the value here. Now Sj dot K is each value here minus the total mean. So when we get that, okay, we say A is the, what do we mean by A? A is the number of treatments. How many number of treatments we have here? 1, 2, 3. So we have just only 3. A is the number of treatments. So we have 3, comma B. So according to this, we can see the final here is just n, which is not specified. So which means our B will be equals to n. That is, how many columns do we have here? 1, 2, dot, represent a lot. Then n, we have B equals to n. So now ANOVA table. The ANOVA table, because the essence of getting all of these is just for us to get the ANOVA table. This is how ANOVA table for one factor experiment looks like. So here we have variation, then we have degree of freedom, then here we have mean square. So we have mean square. Then here we have calculated F. So how do we do this? So but first here we have V subscript B. V subscript B, which is variation. Sorry, this is variation between treatments. Variation between treatment is V subscript B. Variation between treatment, V subscript B. Variation between treatment. Here is V subscript W within treatment. So we have VB, and the degree of freedom is given as A minus 1. That is the number of treatments minus 1. Then the mean square here, we have VB, variation between treatment, divided by the degree of freedom, that is A minus 1. Then second row, we have a variation within treatment, which is V total minus VB. Variation within treatment. So we have the degree of freedom to be A into bracket B minus 1. B is the number of row. 1, 2, we have number of rows. So which means our B equals to n. So the mean square for variation within treatment is going to be VW subscript W divided by A into bracket B minus 1. Then finally we have the total variation. It's a total variation, and this is the formula for calculating the total variation. So the total variation is given us with the degree of freedom will be A multiplied by B minus 1. That is multiply A times B minus 1. Then here there is no need for us to calculate the mean square for total variation, so we're going to leave the space empty. Now the degree of freedom, how do we get the degree of freedom? So we said mean square for variation between treatment divided by, that is this box divided by this box, is going to give us F at degree with degree of freedom A minus 1 comma A into B minus 1. And then what do we mean here? What we have is V subscript B divided by A minus 1 divided by everything that we have here, V subscript W divided by A into bracket B minus 1 with degree of freedom A minus 1 comma A into bracket B minus 1. So this is how to get the ANOVA table in analysis of variance, and this ANOVA table is just for one factor experiment. Okay, let's look at this example. So we have A, B, C, and each treatment has contain 4 observation. 1, 2, 3, 4. Each treatment contain 4 observation. So therefore we say A equals to, A is the number of treatment. We have 1, 2, 3. Therefore our A equals to 3, comma B. B should represent the number of observation in each treatment, and in each treatment we have equal observation in all the treatment here. So we have 1, 2, 3, 4. So therefore our B equals to 4. Our B equals to 4. So before we move on, according to the previous formula, so we are going to need the mean of each value here, the mean of each treatment here. So let me create another column. So let me name this one as total. So 2 plus 3 plus 4 plus 3 will be 12. 5 plus 5 plus 4 plus 6 will be 20. 3 plus 4 plus 5 plus 4 will give us 16. So let's say this is the total for treatment 1, the total for treatment 2, the total for treatment 3. So practically, this is summation x1 for the first treatment. Let's name this with summation x2, summation x3. All these are not needed. I'm just writing it there so that I will understand. Okay, therefore, the grand total for all this observation, we add all of this together, which means when you add 12, 20, and 16 together, we're going to have 48. So 48 is the grand total. All right. So now let's find the mean of each value here. So we say x bar 1 will be equals to the total divided by the number of observation in each treatment. So since this is 12, say 1, 2, 3, 4. This is going to be summation x1 divided by n. And this is going to be, I'll just say, let's use b here since we're using b here. So this is going to be 12 divided by 4. And this one is going to be 3, comma, x bar 2 is going to be this divided by, since we're using the same b, so we have 20 divided by 4, and this will be equals to 5. Then x bar 3 equals to 16 divided by 4, and 16 divided by 4 will definitely give us 4. So now the grand total x bar equals to, see, I do not use any subscript, either 1, 2, 3 to indicate this. Now the grand total, which is 48, this is going to be 48 divided by, now what are you going to use to divide this? Because it is total number of observation we're going to use. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. For this we have 4 observation, 4 observation, 4 observation. If you add everything here, you definitely have 12 observation. So then we're going to have 48 divided by 12. And 48 divided by 12 definitely give us 4. So which means the grand total mean is equals to 4. Alright. So let's start with total variation. Total variation. That is V subscript T. And the formula is given as summation j dot k into bracket x j dot k minus x bar all square. And what does this mean? That is each value here minus the total mean. This is the total mean. You can say x bar, the total mean 4. Each value here minus 4, then we square it, give us the total variation. So we say V subscript T equals to 2. We have 2 minus 4 square plus the next value 3 minus 4 square plus 4 minus 4 square. The mean is the same, x bar is 4. Then we have a plus 3 minus 4 square plus here 5 minus 4 square plus another 5 minus 4 square plus 4 minus 4 square plus 6 minus 4 square plus 3 minus 4 square plus 4 minus 4 square plus 5 minus 4 square plus 4 minus 4 square. So our v subscript t will give us, if you add all of these together, we're going to have 14. So it means our total variation equals to 14. This is 2 square, which is 4, plus 1, 5, is 0, plus 1, 6, plus 1, 7, 8, 0. This is 4. You understand? That's how we got 14. When you add all of this together, we're going to have the total variation to be equals to 14. Okay, variation between treatments. So variation between treatments. Variation between treatments. So we have v subscript b, and the formula is given as b summation j dot into bracket x bar j dot minus x bar all square. So we say v subscript b equals to, our b right from here is 4. The number of observation in each treatment is 4. So we have 4 into bracket. Let me use this bracket. Now x by j, what does it mean? The mean of each treatment, and the mean of these we have it as 3. The mean of the second row we have it as 5. The mean of the fourth row we have it as 4. So what that translates is, we're going to have each mean minus the grand mean, and the grand mean here is 4. So the first one we have 3. So here we have 3 minus 4 square plus the second mean for the second row, 5 minus 4 square plus the third mean for the third row, 4 minus 4 square. Then close the bracket, and this is equals to 4 into bracket 3 minus 4, that is 1. 1 square is 1. 5 minus 4, 1 square is 1. This is 0. So we have what is it called? 1 plus 1 will give us 2. So definitely we have 4 into bracket 2, and this will give us 8. So which means variation between treatment is equals to 8. So now we need to calculate variation within treatment. Variation within treatment, which is a v subscript w. So the formula is given us summation j dot k into bracket x j dot k minus x bar j dot, then whole square. And what does this mean? J dot k minus x bar j, each value in this observation minus the row mean. You can say the mean for the first row is 3. So each value here minus 3, then plus for the second row, each value in the second row minus the mean for the row 2, which is a 5, and that the same thing is going to happen to the third row. So what does that mean? This is how we translate that. We say this is equals to, for the first row, each value in the first row minus the mean of the first row. So we say 2 minus 3 square, 3 minus 3 square plus 4 minus 3 square plus 3 minus 3 square. This is not part of it. Then plus, we've exhausted the first row. Now we need for the second row. Each value in the second row minus the mean of the second row of the second treatment, which is 5. So we say 5 minus 5 square plus 5 minus 5 square plus 4 minus 5 square plus 6 minus 5 square plus, now the third row, we have 3, 4, 5, 4 minus the mean of the third row, which is 4. So we say 3 minus 4 square plus, sorry, is the mean of the third row 4? Yes, 4. So we say 4 minus 4 square plus 5 minus 5 square plus 4 minus 5 square. So variation within will be equals to 2 minus 3, that is 1. 1 square is 1, is 0. 4 minus 3, 1. 1 square is 1. So we have 2. All these are 0. 3, 4, 5. We have a 6. So which means variation within treatment will be equals to 6. Then alternatively, this variation within can be calculated simply as the total equals to V total minus V between. Now, if you see very well, we'll say V total here equals to 14. So we say 14 minus V between, which is 8. Therefore, 14 minus 8 will give us 6. So instead of passing through all this, we can just use this short way to get that. So now we have our total variation to be 14. Don't forget that. Variation between treatment to be 8. Remember that. And the variation within treatment to be 6. So next now we have to prepare the ANOVA table. Let me make it big. It's not necessary to make it big. I just want us to see it clearly. That's why I'm doing it bigger this way. So here now, so we have variation, just like the first slide I showed you, variation. Then the second one here we have degree of freedom, then followed by mean square, then followed by F calculated. All right. The first row in the ANOVA table, we have a variation between. And variation between treatment, just like we calculated before, is 6. So we put the 6 here. For the second row, we have a variation within treatment, just like we calculated from the previous slide. Calculation within treatment, sorry, it's like I've made a mistake here. Variation between treatment is 8, so therefore this is going to be 8. Sorry about that. Variation within treatment is 6, so here we have 6. And finally we have total variation, and total variation right from here is 14. So we have a 14 here. 14. Now the degree of freedom. Degree of freedom here we have a minus 1, and as we know our a is 3, so we say 3 minus 1. We're going to have 2 as the degree of freedom here. Here we have a into brackets b minus 1. A is 3, B is 4, minus 1 from the previous slide. So here now say 4 minus 1 give us 3. So 3 times 3, therefore here we have 9. Now degree of freedom from the total, so we have AB minus 1, which is 3 times 4 minus 1. 3 times 4 is 12. 12 minus 1 give us 11. And if you look at it, if you add this 2 plus 9, you're going to have 11. 8 plus 6, you're going to have 14. All right, mean square. Mean square for variation between will be equals to variation between divided by the respective degree of freedom. That is 8 divided by 2. So if you do this, we have 8 divided by 2. This will give us 4. That will give us 4. Then here we have a mean square for within, and this will be 6 divided by 9. So we say 6 divided by 9, and this will give us 0.6 0.667 approximately. So there is no need for us to calculate degree of freedom, the mean square for the total variation. Now for the F calculated, we say mean square for between variation divided by mean square for within variation, that is this box divided by this box, is what will definitely give us the F calculated. So what does this mean? This is a 4 divided by 0.667. So if you approximate this, if you divide this and approximate it, definitely it's going to give us 5.999 approximately. This is a 6. So it means our F calculated is 6 with 2, degree of freedom 2, comma, degree of freedom 9. You can see with 2,9 degree of freedom. So it means if you want to check the table for F distribution, we're going to check on 2 under 9 degree of freedom in order for us to compare with our F calculated value. So this is simply a way to calculate analysis of variance with one factor experiment. There is a shortcut formula to calculate analysis of ANOVA with one factor experiment, but this particular one is the full formula for calculating ANOVA with one factor experiment.